The history of gravity in math. What is gravity? Gravity is the natural phenomenon by which all forms of mass are brought toward one another, influencing all forms of energy and objects. Examples include atoms and photons, and planets and stars, light, mechanical energy, the movement of the waves and the changing tides, and gases forming stars and galaxies. It's also the force by which objects are able to have a property of weight assigned to them here on Earth to be compared to other fields of that same force. So for example, an object falls on Earth versus an object falls on Mars. Early theories of gravitation. Aristotle was the first known physicist to have a theory on gravity in his book titled Physics. He believed there was some form of natural motion by which objects moved on the physical plane. There was some natural motion that no one understood, that objects just moved of their own accord. There was no force pulling them, it was just part of nature. Lesage, who in 1748 came up with the theory that there was a gas actually that filled the entire universe and influenced everything in it. So essentially, instead of there being a force pulling things, it was more like things were in a big ocean and they were all being pushed around by this huge entity of gas that filled the entire universe. Another theory, which actually was well after what we use today, was an idea where gravity could be attributed to geometry, and this is more in line with research of scientists like Stephen Hawking and things of that, and people of that caliber, where they believed gravity could curve space-time, affect other physical objects around it in that way. So now we get to Isaac Newton's law of universal gravitation, which is the most widely accepted form of gravity that we use in our calculations. So in the year 1686, as part of his published work, Isaac Newton basically said, there is gravity. There is this force called gravity that affects all objects in the universe. So that all particles in the universe are attracted to one another with a force that is directly proportional to the product of its masses. So you see on the bottom left, force equals mass times acceleration. So the force that an object produces is directly equivalent to its mass multiplied by its acceleration, which in some cases may be gravity, which is an accelerant. Now, in the bottom right is the entire formula for Newton's law of universal gravitation, which uses Newton's constant g, and any force given gravitational constant, two masses, and the radius between them. So, for example, if you have two spheres sitting on a desk and they have equal masses, you can find the force that's acting on each other by each of them using the gravitational constant, two masses, and a radius. Radius being the distance between the centers of the two spheres, and the masses 1 and mass 2 being the masses of the two spheres. Now, this gravitational constant g was first measured by Henry Cavendish in the year 1797 as part of a large experiment. The device used is called a torsion balance and had been passed down through 2 generations of Cavendish's colleagues before he found a way to implement an experiment. Through tests and rigorous calculations, the now accepted value of 6.74 times 10 to the negative 11th is now used as a substitute for the variable g. The picture in the bottom left is a picture of this torsion balance where two masses were hanging and would spin in circular motion. So, how is gravity used in math? Well, in mathematics, gravity is used during calculations mostly regarding physics and vectors such as acceleration. Surface gravity, known now as little g, not big G. Surface gravity is acceleration due to gravity that acts upon an object on a planet's surface. So every single object on Earth is affected by gravity. And 1 g is equivalent to 9.81 meters per second squared, which is where we get our acceleration due to gravity on Earth. So the surface gravity of Earth is 1 g. different planets have different surface gravities, allowing for mathematical calculations to be done as if they were on different planets. So for example, someone drops a ball on Earth. The acceleration due to gravity is negative 9.81 meters per second squared. However, on a different planet like Mercury or Venus, the acceleration would be different because Mercury's surface gravity is only 0.38 Gs, so it's only 38/100ths of Earth's surface gravity. Or, for example, say Jupiter, which is 2.53 Gs, which is 2.5 times Earth's surface gravity, much larger. Basically, that's all there is. Gravity is essentially what gives physics physics. Without gravity, there really is no physics, and there is no way to calculate motion without gravity, because gravity influences all motion in the universe.